as I mentioned earlier, we were interested in figuring out what is the heritability of the UBO trait across these different mating strategies. Okay, thank you so much for the introduction today. So I'm going to be talking a little bit about some of our research on using UBO assay. And if this is a new word or tool for you, we'll be explaining what that means as a selection tool in bee breeding programs in Vermont. And I like to first off always thank all of the folks who helped me with this work, including my co-authors, field technicians and partners, and then funding sources, with a special mention to Sydney Miller at the top there, who and depicted on the right here, who's our lead technician and now my master's student and leading some of the work that I'm going to be sharing today. She knows, in many cases, much more about this work than I do. So we'll get through it. So for those of you who aren't familiar with the Vermont Bee Lab, I thought I'd start off by just explaining a little bit about some of the projects that we work on. I think that we do a lot of research, but a lot of this research is extension type work where I feel like we're unique in some ways because we work so closely with beekeepers where they help to design research projects. They inform what kind of questions we're asking, and then we oftentimes will work alongside them to write grant proposals and do that work all together. And there's some great benefits to working so closely with the beekeepers in our community. And then there's also, of course, challenges, and we can talk a little bit about that as we go through this, because we're working within the we're working within the confines of their operations, right? We can't say, hey, don't treat all your colonies this year for Varroa mites. So, for example, but we'll talk about that later. So the big project that we'll be talking about today is the Supporting Vermont Bee Breeders, or I should be calling Support Vermont Bee Producers, with UBeeO, and that's been going on since about 2022. We also manage Vermont's involvement with the National Honeybee Survey, which is a USDA APHIS-funded project that's been around for a long time now, and the goal of that is to gather baseline data on bee disease pathogens and also pesticides. We've done some work with beekeepers trying to better understand forage resources for honeybees throughout the state. This was a project that was actually led by an undergraduate student, which is now kind of expanded in forming our state beekeeping association, working towards a Vermont honey certification program, which is really awesome to see how that's evolved. Again, working so closely with them on that. And we also have a pesticide monitoring project that we started in 2021. And it's sort of become a community science project where beekeepers are collecting samples of pollen and sending it to us, and we get their pollen samples tested by the Cornell lab for different insecticide residues. And much of the work that the results that have come from that, both the beekeepers and myself have testified and share those results with legislators, which in turn informed policy in Vermont, making Vermont the second state in the nation next to New York to ban the use of neonicotinoid insecticides. And I think a lot of that work, there's so much pesticide residue and neonic literature out there, but for some reason our legislators really needed to see that bees in Vermont were exposed to neonics, and that's with the help of a network of beekeepers throughout the state. We were able to collect lots of samples around corn and soy that helped to inform legislators on that topic. So it's been an incredibly fruitful collaboration with the beekeepers in our state. We also have a diagnostic clinic that's open year-round where we accept samples from live and dead-out colonies. And we do Varroa and Nosema testing for those beekeepers. It's free of charge. And I will say that I think most of the samples that are submitted to our diagnostic clinic are, not surprisingly, from hobbyist beekeepers who have the time to collect those samples and send them in, or who might not know how to, surprisingly, might not know how to do an alcohol wash or how to identify a Varroa mite. And so this diagnostic clinic is actually turned into sort of an education opportunity where we can work with beekeepers and say, hey, this is what your mite loads are, and these are your options. Um, but we wanted to, now this is where I start transitioning into the meat of our story here of this particular presentation. So we found that our diagnostic clinic was really supporting hobbyist beekeepers, but we felt like maybe there was an opportunity to work directly with our bee producers in the state, because those are the beekeepers who are supplying the bees to all of the hobbyist beekeepers, right? And so if we can go right to the source and support them to produce more disease resistant bees, then we're, you know, getting more to the root of um, of the issues there. We have a lot of amazing, in some cases, world famous bee producers in our state. And so in this case, it wasn't really, we're not going in there telling them what to do. They know a lot more about the day-to-day operation and beekeeping and bee producing than we do. Our goal was to just leverage our lab's resources to help them to improve the quality and availability of locally adapted pest pathogen resistant honeybee stock in Vermont. And so because we have the ability to go out and work alongside them in the field, give them field and lab support, be able to do Nosema tests, help them with alcohol washes, and do some of this hygienic testing, which I'll get into in a minute. We also had this opportunity to support them with a novel hygienic behavior test called the unhealthy brood odor assay, or the UBeeO assay. And I'll be talking about that in a minute. So the objectives here, and I mentioned this already, but to provide field and lab support to select bee producers. I wrote bee breeders, but you know, there's getting to semantics there. Not all of these beekeepers are doing instrumental insemination. A lot of them are open mated. So we're going to say bee producers here, to support bee producers and to evaluate their daughter colonies. We also had an opportunity to do a little bit of R&D, research and development, on this UBeeO assay because it was brand new at the time. It hadn't been made available to the public. And so we had an opportunity to test heritability of this UBeeO trait across different mating strategies. And throughout this whole process, provide pest and disease diagnostics to beekeepers, which will in turn help them to inform their selections for breeder colonies in subsequent generations. So I'm going to back up here for a minute and talk about hygienic behavior in honeybees, because we need to know a little bit about this before we can talk about UBeeO. So hygienic behavior is regulated by chemical communication. In developing brood, developing brood will signal their health status to adult nurse bees. And in a hygienic colony, this will trigger bees to start uncapping and removing that brood. They're essentially saying, ooh, there's something wrong with this, let's investigate, and they start opening those cells. And this can be helpful for brood colonies that have brood diseases. They're sort of keeping track of and removal of those infected or infested brood. And it also can be an interruption to the Varroa mite cycle. And so we know that Varroa mite goes in there, they reproduce under the pupal cell cappings. And so by selecting for hygienic bees, this selective breeding can offer a sustainable long-term solution for Varroa control. And I'm sure this is a review for many of you, but maybe there's some new beekeepers that this is here, and I'm happy to share a little bit about hygienic behavior and how it's been used, how it's been tested in the past. So there's some of the methods of hygienic behavior of testing for this behavior include the use of liquid nitrogen. So in this case, you would find a frame of capped brood. You would put a PVC or some collar over a section of capped brood. You would pour liquid nitrogen over that section of capped brood, and then you would give that frame back to the bees for 24 hours. You would return to that colony and pull that frame and count how many of those cells were opened up where the pupae have been removed. And so in this case, you're testing the bee's ability to detect and remove compromised, or in this case, dead brood, because that liquid nitrogen will kill that brood underneath those pupal cappings. And if you have a colony that in 24 hours did a really good job of uncapping and removing those pupae, it's 95% of those pupal cappings have been opened and where the pupae have been removed, then you can say, ooh, I have a high hygienic colony, and that might be a colony that you would want to select for. So you would take, you would rear queens from that colony, and then you'd have, so you'd have your breeder stock there. And so this has been a method of testing for hygienic behavior in the past, but it's pretty, it can be labor intensive. It can be a little bit of a barrier to getting and to transporting liquid nitrogen around. And research has found that it doesn't always confer Varroa resistance. And so just a couple years ago, Dr. Kara Wagoner, a collaborator of ours from the University of North Carolina, Greensboro, there's a lot of great video footage online about UBeeO at this point. You can check out InsideTheHive.tv. He did a good interview with her about this if you want to learn more about UBeeO. So in over, I think it started maybe in her PhD, but she developed a new method for testing for hygienic behavior. And what it involves is a blend of synthetic pheromones that mimics diseased brood. And so you spray, and rather than putting liquid nitrogen on an area of pupal cappings, you would spray this mixture of synthetic pheromones on an area that you've isolated with a PVC collar. And then you would give that frame back to the bees for about 2 hours. So the 2 hours instead of 24 hours, right? And then you return and you look to see how many of those cells have been manipulated. And so here's a great example of what we would consider a low UBO colony. So in this case, that colony did not detect or didn't care about the smell of diseased or dead brood in this case. And so we have a before picture here and then an after picture here. So you can see it looks the same. There's no cells that have been manipulated, in which case we would call this a low UBO colony. As opposed to this example here is before and after picture, where you can see that nearly all of the cells have been manipulated. And for UBeeO, it's a 60% threshold. So if 60% of those cells have been manipulated, then you have a high scoring or a high UBeeO colony. And some things that I'd like to note about this is that with the UBeeO, with the hygienic or freeze brood assay, which I mentioned before with using the liquid nitrogen, the freeze brood assay, or freeze kill assay, you also hear that sometimes. You are counting cells that where the pupae have been completely removed, but with the unhealthy brood odor assay, you're sort of just tricking the bees into thinking that there's something wrong, right? Because there isn't. And so in this case, bees will start to investigate. They might start uncapping, and then they might go, oh, actually, there's nothing wrong with this pupae, and they might start recapping again. And so because of that, the brood aren't dead in this case, like it is with the liquid nitrogen. That's why there's this 2 hour that Kira has determined that there's a 2 hour point, because if you wait longer than that, the bees might start recapping the cells and you would miss that signal. Additionally, you're only looking for cells that have been slightly manipulated. So even a pinprick of manipulation counts in this case, because they've recognized something and they started to uncap it. And so, yeah, I think that's all I'll say about that. And when you order UBeeO, it comes with this spray gun here for administering it. And so we found it to be very simple to use in the field. We like not having to use liquid nitrogen. We really like that this can be super rapid, where we get all our results in the same afternoon. And so here's are some of the advantages and disadvantages here. They are available now for purchase at Optera. I mentioned these here. So the testing for response here is that we're looking for the bees are responding to stressed brood, not dead brood. So it's thought to be more reliable test. It's quicker, so it's that 2 hour versus 48 hour. I gotta tell you, the energy in a bee yard when you're working alongside these bee producers and you're getting high UBO colonies, and it's like almost immediate results. We test, we eat some lunch, and then we go back, and it's like it can be such a fun activity and fun afternoon to do with these bee breeders or these bee producers in a day. But one of the disadvantages is that it can be sort of expensive, and I don't know what the cost of it is going to be this coming year, but in the past it's been up to $30 a test. So I think Kira is working hard to try to get that cost down for beekeepers, because that is a big barrier for some people. So now I'm going to talk a little bit about how we're using this with our bee producers in our state. Um, but I'm going to back up and talk about how we started working with them. So this is many of you might have heard or maybe know him, Mike Palmer. He's a long running bee producer in the state of Vermont. And we started working with him a few years ago. And the goal here was to just leverage our lab's resources to help add some more metrics in where we can look for Nosema virus, hygienic behavior, and Varroa load. And so he had been selecting for honey production, brood production, overwintering success. And our goal was to kind of add these additional metrics in to help inform his breeder selections. And we got a small SARE partnership grant to do this work. And it was only for 2 years. And so we thought, well, we don't know what we're going to be able to see a difference, when you're selecting for these traits, like how many generations is it going to take? We thought, we're going to only be able to do this for 2 generations. Are we going to actually see a difference? But this would be the start of something bigger and sort of like a pilot of how our groups might work together. And if it worked, then we can keep up that relationship. And so we started with evaluating 100 hives and made selections into 2 groups. And so in this case, we sort of had a control group because we wanted to compare how far along we could get with our selection criteria versus the selection criteria that Mike had been using previously. And so our 2 groups consisted of FHA, which we call French Hill Apiary Queens, and those were selected based on the traits that Mike always selects for: honey production, brood production, overwintering success. And then we have our groups of colonies that were requeened with queens that are new project queens, NPQs. And those were selected for all the things above, but also those additional metrics that I mentioned: Nosema virus, hygienic behavior, which initially was tested with freeze brood assay, but we eventually switched to UBeeO and Varroa load. And this was a 2-year project, just followed for 2 generations. And so we're like, okay, well, what are we going to find? Well, in just 2 generations, we found that. So these are figures showing Varroa prevalence and Varroa mite load. We found that mite loads were lower in the new project queens over time. And so they definitely went up later on in the season, as they always do. But the new project queens, even after 2 generations, the mite loads were statistically lower in our cohort of new project queens, which was really surprising to us to do that so quickly. And then we also, just after 2 generations of looking at UBeeO, using this novel assay for hygienic behavior test, or novel assay for hygienic behavior, we found that in just a couple generations, we were already able to select for colonies that had higher UBeeO scores. And so these 2 bars are showing, these are the UBeeO score. So the y-axis is UBeeO score. And then these are the French Hill Apiary queens that were not selected for hygienic behavior. And then this is just 2 generations later with their new project queens. You can see that on average, there were more colonies that were scored high UBeeO. And this dotted line here, which you'll see throughout my talk here, is representing colonies. Anything above that are colonies that are considered to be high UBeeO colonies or high hygienic colonies. So just in a short amount of time, we were able to see some results, which was cool. So once we started to get our hands on, you'll see that this is almost like a story at this point. Once we started to get our hands on UBeeO, and it was at this point not available to the general public, we were working directly with Kira, and she said, hey, yeah, I'd be happy to sell you some UBeeO if you're going to work with these bee producers. As soon as the word got out, we had other beekeepers in our state who said, we'd love to get involved and work with you on this and get our hands on some UBeeO, and you're happy, we'd be happy to participate, and maybe you can learn some things in the process. And so we applied for a grant that we got called Supporting Bee Breeders. And this was with Mike Palmer again, and Andrew Munkhurst from Lemon Fair Honeyworks, Jack Rath of 100 Acre Wood Apiary, and then Bianca Braman and Adam Collins joined on as well, a little bit from Vermont Bees. So these bee producers, they have a range of sizes and management strategies, which in some way made it a little bit challenging, right? To try to, as a scientist, you want things uniform. You want to be able to compare your results across different yards and operations. And if everyone's doing different things, that can make the data really noisy, right? But on the other hand, we had to keep our eye on the prize, which was no, the point of this work is to support the bee producers in our state. And then any data that we can glean on top of that is going to be cherry on our pie. And also, hey, we have a really cool opportunity to look at how all these things or all these things are measured, all these things that we want to measure across different management strategies and operations. So so that was sort of this perspective that we met this project with. And so these bee producers, they range from 150 to 1,000 hives. They range from 300 to 1,500 queens produced. And some of them use only open mated mating strategies where those queens are mating with drones out in the wild. And then the other beekeepers are controlling their genetics with instrumental insemination, where they're collecting drones, harvesting that semen, and inseminating queens. And so because of, so our first off, we said, okay, are we going to be able to find in our first generation of cohort of all these beekeepers, are we going to be able to find any high UBO scoring colonies? And this was, the first step, because if we were able to find high UBO colonies, then we had, a lot of opportunity here to do some R&D on UBO. We could select for it. We can look at how heritable this trait is. We can compare UBO scores to different pathogen loads, and all of those data I'll be sharing with you today. But this was really the first step. And so this is the first generation cohort of our participating beekeepers, and this is the UBO score. And so I like to show this slide because if someone is interested in starting the process of using UBO or hygienic behavior testing, this might be what you expect. So the line here again represents any colonies above this line are high hygienic colonies. And so, and the dot here is the average UBO score for each of these first generations, and each bar represents a different operation or a different cohort of first generation before we started selecting using the UBO assay. And so you can see there was quite a range, right, of UBO scores across, but there was a lot. In every instance, we had high UBO scoring bees, which was great because it meant that we could continue forward with looking at heritability. And I will note that there's some operations had a lot more high UBO scoring colonies in the first generation, and that was because those beekeepers had already been using the freeze brood assay. And so what we find, if you've already been using that assay, you probably already have a lot of hygienic colonies in your yard, and you're gonna find that that they're gonna score positive with UBO. And that's what we saw here. Okay, let me skip ahead here. So as I mentioned earlier, we were interested in figuring out what is the heritability of the UBO trait across these different mating strategies. And so we had, bear with me here, so II is instrumentally inseminated. Those are queens that are inseminated with drone semen that have been harvested from drones. And and then we have open mated queens that have gone out and mated with drones out in the wild, right? And so we created these 4 different groups of queens that were instrumentally inseminated from high UBO instrumentally inseminated mothers. So this is like double II. So in this case, you would expect if their mothers are high II and then those queens were instrumentally inseminated themselves with high UBO drone, that's supposed in our, we hypothesized that they would be most likely to reproduce daughters that were also high UBO, right? That's where in the instance where we would most likely see that this trait is heritable. And then we had a group where these queens were open mated and they were from high UBO instrumentally inseminated mothers. We're calling those IIOM. And then we have queens that were open mated and they had from high UBO open mated mothers. So their mothers were found to be high UBO scoring colonies, but those mothers were open mated. And then we had OM low, which was mothers are queens that were open mated and they were from mothers that were found to be low UBO as sort of a control to see how heritable this trait is across these different groups. And the goal here was really to try to see, this was the one that we were most interested in, the IIOM. because for our bee producers, it's way too labor intensive, right, to instrumentally inseminate queens. And those queens are so valuable to them, they're not going to be able to, nor would they want to sell them to hobbyists or other beekeepers, right? Their goal is to get their instrumentally inseminated high UBO queens, and then have them produce open mated daughters that they can sell to other beekeepers, that they can say these were from high UBO colonies, and so therefore those are likely to be high UBO themselves. And so this was really what we were most interested in from a practical standpoint of if beekeepers are incorporating UBO in their operations, how easy is it for them to produce and market high UBO colonies to other beekeepers or to the general public, right? And so these are our results. So this is showing the UBO score of the daughters of each of these groups. And just as you might expect, like this is this is exactly what we expected, right? So we found that more daughters had higher scores the more instrumental insemination that was done, right? Like that's kind of a no-brainer. But it meant that our design here worked, and that we found the lowest heritability in queens that were open mated that had low UBO mothers, right? So this is just by chance we might end up with a high UBO colony in this instance because we're not really selecting for it in this case. But so if we're most interested in this group here, like because of all the reasons that I mentioned in the previous slide, only 16% of the daughters that are open mated that are produced from an instrumentally inseminated mother were high UBO themselves. And so this indicated to us that beekeepers really can't, at least based on these preliminary results, like a beekeeper shouldn't feel comfortable producing daughters from a high UBO colony and then marketing them outright without testing them. And so our beekeepers who are interested in selling high UBO queens, this is a caveat that they're telling folks, or we're helping them to test the daughters as they're being ready to be sold to confirm whether or not they're high UBO. But I will note that there are some caveats to these data, and that's what I'm getting into this point here. So we saw lower heritability than expected in subsequent generations. We also had this really interesting phenomenon that we've really tried to figure out. We did a lot of work last year, where if we test the same colony over and over again for UBO, in May, it might be negative, like it might be a low UBO colony, but then we retest it again in June and it's a high UBO colony. So their response is changing to these synthetic pheromones. And we're trying to figure out what are the internal and external factors that influence hygienic behavior performance. And right now, we get the feeling based on our data from discussions with Kara that what we're seeing is false negatives. So what I mean by that is if a colony tests positive if a colony scores high on a UBO test, it means a high scoring UBO colony. If it scores low, it may be low, but it could also be high, and that the environmental conditions aren't quite right. And so we know that bees aren't so responsive to the test when there's a nectar dearth. And so some of the recommendations that are coming out of this is if you're going to be doing the test, to feed your bees with sugar water or sucrose up to a week before you perform the test, to give them a little bump, and then that will provide greater reliability in the test. We also have found some really interesting things where we had two apiaries in one of the yards, where one apiary, and they were all from the same breeder lines, they were all from high UBO mothers, and we were testing the daughter cohorts. And one yard had an EFB outbreak, European foul brood, and the other yard did not. And in the yard where there was the EFB outbreak, we had over 70% of those colonies with high UBO scores. And in the apiary that did not have EFB outbreak, we had fewer than 10, I think it was around 10, 15% of those hives scored high UBO. And so we believe that there's what I'm calling a pathogen priming response, where sort of if a colony is in a yard or nearby or has been exposed to a pathogen, you think about how your immune system might turn on high alert, and then you'd be the bee's response to unhealthy brood assay or to the scent of unhealthy brood might be higher in the case when they've already been challenged with a pathogen. And so we have a grant proposal in with SARE, looking into those things, looking into the potential for pathogen priming and the internal and external factors that influence this. And then also better understanding, so the ratio of hygienic drones needed for successful instrumental insemination and heritability. We know that we need to follow the drone origin better with this instrumental insemination work that we did previously, and because we know that drones will drift, right? And so we're going to be working closely with our beekeepers to look into this a little bit better and trying to control that drone origin. So now I'm going to talk a little bit some of the results comparing the UBO scores and the different pathogens that we looked at. So it's great to be able to find a hygienic colony, but how good is that hygienic colony, or how good is that high UBO colony at withstanding, tolerating, resisting pathogens, right? And so in the case of Varroa, this here are results from our Vermont beekeepers. We find that hygienic colonies through the UBO assay have lower Varroa prevalence and load. And so, and this figure is showing prevalence, and I'll start here. What I mean by Varroa prevalence, I mean the proportion of colonies that are positive for Varroa mites. So some colonies did not have Varroa mites early on in the season, and then of course it eventually over the course of time, this is month here at the bottom, most of the colonies all had Varroa mites, as one might expect, but we saw that in high UBO colonies, fewer of those colonies had Varroa mites over time. In this figure here, we're looking at Varroa load. So this is the number of mites per 100 bees. So how severe is that mite infestation? And the blue line again is the low UBO colonies, and the purple line is the high UBO colonies. So those are high hygienic colonies. And what we found is that our high UBO colonies are better at keeping their Varroa mites load down longer in the season. And then in September, boop, they all just pop up really, really high. But what I'd like to mention and make note of, and this is important, is that the dotted line here represents our treatment threshold, which we set for 2 mites per 100 bees. So that's the point at which we said to the beekeepers, okay, you can treat. You can see that those high UBO colonies stayed below that treatment threshold much longer, all the way until September, whereas the low UBO colonies, they bumped up above that treatment threshold in July. And so, by using this assay and selecting for hygienic behavior, the goal here is, of course, as you guys all know, as part of this group, is to reduce the reliance and use of miticides. And in this case, it looks like, it's pretty successful. Like we're holding out longer with those high UBO colonies until this point. And I also want to mention, because we're working, the goal here is to support these bee producers. We have to keep reminding ourselves that that's been the goal, is to work within their operations. They're trying to make a living. They're working their own bees. They have their own goals. And then we're just trying to collect data on top of that. And so because of that, when we had a high mite load colony, we weren't able, in August, September, we weren't able to move that colony away from the others to try to isolate it. Everyone was just in the same yard. And so I'm really curious to see how these high UBO performing colonies would do if they weren't next to or in the same yard as the low UBO colonies, because it's likely that the mite pressure just became so high, and there was no isolation where they could get away, and we know how mite bombs work, that they were just sharing mites at this point. So in the future, if we were able to better control for that and keep the high mite load colonies away from the high UBO colonies, I would be really curious to see how they would perform later on in the season, if they would continue to keep their mite loads down. So we have a paper in review with a number of researchers, and the goal of that, looking at using UBO across a wide range of pests and pathogens, comparing pest and pathogen loads to their UBO scores. And it was done in 4 different geographic areas, including Australia. And we were just seeing at how UBO, and we're thinking of it sort of like as a case study. And so we looked at Varroa, chalk brood, RNA viruses, and Nosema, which we are now calling Veromorpha, right? And we find that UBO predicts lower pathogen loads in all these cases, which has been really interesting. It's not just for Varroa. And here's a figure showing some of the results from the virus work. And this was done with Kara Wagoner, Corinne from Australia, and Ismail Amari from University of Mississippi, and Sydney Miller and Alex Burnham from the University of Vermont. And here we're looking at the UBO score on this axis, and this is the virus load over here. And these are six different viruses of interest. And the green line represents statistically significant correlation here, and this dotted line is showing that there isn't a signal. And so we found with higher UBO scores, we find lower virus loads. And so that's what all these lines, these negative correlation lines are showing here. And so the higher the UBO score, the lower load you would expect in deformed wing virus A. B is really acute paralysis virus and lake cyanide virus, whereas there wasn't a correlation here in black queen cell or sac brood virus. Okay, so we also found this really interesting result here in Vermont where hygienic colonies have lower Nosema loads over time. So Nosema prevalence didn't differ between high UBO colonies or low UBO colonies, but load did, is that over time the high UBO colonies, which is depicted in the red, had lower Nosema scores over time, or Nosema loads over time. And then this is another way of depicting that same result where you get rid of the time element. So you're just looking at Varroa load compared to UBO score. You see there's a relationship here where the higher the UBO score, the lower Nosema load. And I'll explain in a minute. I'm going to summarize what I just shared all with you, and then I'm going to explain a little bit more about this and why this is such an interesting result, and then some of the work that's come out of that. Okay, so to summarize that, we have an average. So if you're using UBO for the first time, you can average around 20% high UBO colonies in an unselected generation. That might be what you're expecting. This is our average because we're looking at beekeepers who've also been using the freeze brood assay to select for hygienic behavior. If you haven't used that before, we're looking at a little bit lower, more like 13%. Of colonies in your operation would be high UBO performing colonies. We found better heritability in daughters using instrumental insemination with those caveats. Hygienic colonies have, through the UBO assay, have lower pest and pathogen loads, and it's appearing that the UBO is a promising new tool for bee producers to select for hygienic colonies with not just Varroa, but other pathogen resistance. Okay, let me just... Okay, so back to this result about Nosema load and why it's interesting. Do I have it here? Okay. So Nosema is a pathogen of adult bees, not of brood. And so we were really interested to find this because we know that hygienic behavior and the way that the UBO assay works is that you're testing the bee's ability to detect and remove diseased brood. And so in this instance, if bees are keeping their Nosema loads down, and Nosema is not a brood pathogen, then these high UBO scoring colonies are doing it in a different way, because the mechanism of them removing brood in this case, wouldn't help them reduce their Nosema load, because brood simply they don't have Nosema, it's just in adults. And so my graduate student, she's been my tech for a long time, so it's hard to make that change in color, my graduate student here. But so Sydney Miller thought this result was really interesting, and she wanted to design an experiment to look at how hygienic bees are as tested through the UBO assay, but I'll be calling them hygienic bees at this point, how they are keeping their Nosema levels down. And her project consisted of 2 phases, because honeybees either express disease resistance on 2 different levels. One at the innate immune function of the individual bee, and also as a superorganism, right, that can engage in social defenses like hygienic behavior that combat diseases in the colony as a whole. And so here she's evaluating the potential mechanisms of, and I'm going to keep calling it Nosema because Nosema got reclassified as Veromorpha, but just for simplicity's sake, let's just keep calling it Nosema. Mechanisms of Nosema resistance demonstrated by high-scoring UBeeO colonies. And so first thing I'm going to be talking about is her results that she found of this first phase of resisting it at the individual level. So her experiment consisted of 4 high and 4 low scoring colonies that she pulled of individual bees from to test their individual immunity. And she put them into, let me see, she administered Nosema inoculant in 3 different doses. Either a control group that got 0 spores, so it was just a sucrose solution. Some of those cups got 10,000 spores per bee, and then which is a low dose of Nosema, and then a high dose of Nosema of 50,000 spores per bee. And then she had multiple replicates of each of those. Newly emerged adults were reared in the lab, and they were fed the inoculum for 24 hours. She had 30 bees per cup. And then over the course of 12-day infection period, 4 bees were extracted every 2 days. So she could follow what the Nosema infection level was over time from bees that were either from high UBO colonies or low UBO colonies, right? And then she used PCR to assess the level of Nosema infection in the RNA of individual worker bees. So then she looked at Nosema loads over time. And so I'll walk you through this figure here. This is Nosema score on this axis. So this is the amount of Nosema, or relatively, but for purposes of simplicity, this is the amount of Nosema an individual bee has. And this is the infection period, so over time. So this is 4 days, 6 days, 8 days, 10 days, and 12 days when she ended her experiment. And so at 0 spores per bee, so these were all the bees that were fed just a control. There was no Nosema. That was great, meant her control worked. We were very excited about that. And then in the instance of when bees were infected with 10,000 or 50,000, we saw that the infection level increased over time. However, there wasn't a difference between the bees that were high or low UBO scoring colonies. So it's hard to see because the similarities they're so similar, but those 2 different lines are almost following the same path. She was excited by the fact that she was able to, Nosema is notoriously difficult to work with in the lab. And so this was the first time that she had, actually our lab had worked with it in a lab setting. And so we were excited at first to at least be able to show like the experiments working, we're infecting bees as we predicted, right? And let's see. Yes, and that's another way of displaying the data here, just looking at high UBO colonies and low UBO colonies and their infection levels over time. I'll skip that. However, something interesting that she found was that the high UBO bees consumed less of the inoculum. And this became more significant with the more Nosema that was in the food. And so we have high UBO colonies here and low UBO bees here. And the difference in the amount that they consumed is not significant, which is depicted here, NS. In the case of when it's just 0 spores per bee, the control group. But when bees were being fed 10,000 spores per bee, we see a statistically significant difference in the amount that was eaten, where the high scoring bees ate less than the low scoring bees. And we see this difference even more, which is depicted by more statistical significance, when there's even more Nosema. So what does that mean? Well, we'll get to that in a minute, but it's looking like that these high hygienic colonies are not only better at sort of sniffing out their diseased sisters, but they're also better perhaps at sniffing out diseased food, right? Food that's been infected. So we also looked at the probability of bee survival. So if you are not used to looking at a survivorship curve, I'll walk you through this. This is the percent of bees that have survived in the cup. And then at each day, she counted the number of bees that survived, or, counted the number of bees that died and subtracted that, right? And so if we had all bees, and then this is time over time. So 0 days, 5 days, 10 days, 12 days, the end of the experiment. And so if you had all bees survive the entire experiment, right, you would just have a line right up here across the 100%. But over time, as you would expect, bees aren't used to living in little cups, right? And so they would die over time. And so the different colors of the lines represent the amount of Nosema that they ate over time. And so bees that had just the control, there was definitely some attrition, which you would expect anyway over time. But we found that bees that consumed the Nosema spores died earlier, right? And that's what the red and orange lines are representing. It's almost identical, whether they had 10,000 or 50,000 spores. There was more death that occurred earlier on in those bees that ate Nosema, which meant, okay, the experiment worked, the Nosema is affecting the bees, the infection is occurring. Now, when we break this out by high and low UBO colonies, what we found was that high UBO colonies were more likely to survive. So despite having the same level of infection, they were more likely to live through it, which is more indicative of a pathogen tolerance, right, than a resistance. They're not just resisting it, they're tolerating it. And so bees from hygienic colonies may be, better able to detect and avoid contaminated food sources. Something that I don't have time to show you today, but her work is also looking at upregulation of VG, which is a precursor protein and general health indicator. So bees that were from hygienic colonies had upregulated VG, which may limit the health impact of the Nosema infection. And so it's appearing that maybe they have enhanced tolerance to Nosema and they're better at avoiding it. So the last couple slides here are just going to show you a little bit about the social defense at the colony level. So the second half of the experiments that Sydney is working on, she looked at this individual level, and now she's curious about what are these high UBO colonies doing differently at the social level. Are they removing adults that are infected, for example, in addition to removing infected brood? And so her methods here, oh, I can play a little video for you too. Let's see. Her methods of this, we did some preliminary work last summer where she inoculated newly emerged adults from both high and low UBO colonies with Nosema. We marked those bees and then reintroduced them to the original colonies. And we went back through each frame and looked at every bee to assess the probability of colony acceptance by recording the number of infected bees remaining in the colony at day 3 and day 10. And what we found was that this is really preliminary, but we retrieved fewer Nosema infected adults in high UBO colonies, which is indicative that maybe those colonies are less likely to accept those Nosema infected adults and are better at distinguishing um, infected uh, infected bees over healthy individuals, which is great news because it means that this is not just happening at the brood level, but it could be happening at the adult level, which is great for pathogens like Nosema that affect adults and not brood. And so in the next summer of 2025, we have plans to conduct observational experiments to really get an idea for whether these bees are being rejected or what's happening to them. Why are they disappearing? And how are maybe they're getting escorted out of the hives, or what. We have to try to understand what that behavioral mechanism is that's at play there, that's resulting in fewer Nosema infected bees in the hive. So all of this information that we've gathered and collected over the past few years working with UBeeO and our bee breeders, we've put together some fact sheets that are available on our website that you're welcome to take a look at. And we also have been doing workshop trainings. We had a lot of interested beekeepers in our state when they started to hear we were using this novel hygienic assay. And so we've been offering hands-on workshops for beekeepers, showing them how we're using it and teaching folks. And so if you want to learn more about those workshops and any of our research, you can visit our website, and that QR code should bring you right there if you're interested. And thank you so much for listening to me, and I'm happy to take any questions.
Well, thank you so much, Dr. Alger. I appreciate that very much. We have a whole slew of questions. Some of them are a little lengthy or may have been answered during the presentation. Let me see. I'll cue some up here.
A lot of questions about pathogen priming, I see.
Yes, yes.
Cool. Yeah, I
Someone
think it's
spotted a video from one of our past presentations a few years ago that talked about it as well.
oh, if someone could send that to me, that would be great. We haven't dug in much doing like a full literature search on it. So if you want to send me everything you got, I'd be interested in reading about it.
Sure. Was there any change to the UBO score in a queen's second season? I think you highlighted that on the follow-up when you tested the daughters. So I think that would be relative to that.
Yes, so not just her daughters, but you're asking in this case the same queen in her second season. Um, In some cases, yes. In some cases, no. So we were really encouraged because we were in one of Mike Palmer's in his breeding yard, and we had I think 7 or 8 of his breeders all lined up in a nice row, and we tested all of them, and they were all high UBO the year prior. And we tested all of them, and they were all high UBO 100% that year. And so we are like, awesome, super consistent, great. Um, and then the following year, we were at a different operation and we were retesting bees. And because those bees were, yeah, they were nukes the year prior and now they were full production colonies. And we were trying to double check them to be able to select them as their new breeder cohort. And we tested them in May, and we got very few examples of when they were high, like they were high UBO last year, but that year, the year later, they showed low UBO. But then we waited a month in June. I sort of explained this a little bit, but we waited a month and we retested them in June, and they popped back up. Most of them popped back up to high UBO scoring colonies. And so this is getting at the question of this false negative, perhaps, and what are these environmental conditions that might be influencing it. And we really think that in the case of the May June thing, it was related to a nectar flow. And by waiting a little bit longer um, for a little bit more of a nectar flow to be occurring and the weather to be better, we were able to get those scores up, or and for it to be more reliable and compared to the year prior.
That kind of begs the next question just a little bit, because as UBO has gained traction, if you will, people are using it. We're getting more information and feedback from other beekeepers as well as researchers. Kelly Baggett says there's some research and observation indicating high BSH colonies pick up BSH specific hygiene activity during dearth periods or in the fall. So if the test is designed to mimic a parasitized brood, have you tried testing UBO in the fall? Maybe that would lead to less false negatives.
We have tested it in the fall. Yep. And our most reliable time in Vermont is in June, um, is what we're finding.
As far
Which
as
which is
consistency.
as far as consistency, yeah, and consistency with how it confers lower Varroa loads and other pathogen loads. Yes. Yeah, and I think it's in some ways good because it allows for the beekeepers to, so the way that our bee producers are have sort of come around to using it is we were testing in the fall because we wanted to get an understand for what the daughter colonies looked like, for the heritability aspect that we were measuring. But but for the beekeepers, they're like, why are we, let's not use the test in the fall because we have to wait for overwintering losses. We might be, putting all this money out into this test now and doing all this work when really half of them aren't going to maybe not make it through the winter, or a portion of them won't make it through the winter. We should really just the test as the final sort of metric for right before we select breeders in the spring. And so that's sort of like, we were doing some testing in the fall just for our own R&D and interest, but the beekeepers, if going forward, that's when they want to do it, is just in the spring as their final test. And that way they've got a full overwintering period. They have all the data from the year prior on the Varroa mites and Nosema and viruses, or any other metrics we're using. And then we use the test at the very end to make our final decisions.
Yeah, that's where I think the data is going to be most valuable, at least from the practical and application standpoint. So that's
Exactly,
we
yeah.
want to focus that. Greg from Indiana asks, did you do any parallel testing to determine the correlation between the freeze kill assay and the UBO assay? Is the pheromone profile the same between dead brood and unhealthy brood?
I know Kara has, and actually see that Kara is on the chat. So Kara,
We'll
if
chip that over to her.
yeah, if you want to unmute yourself, you're welcome to take that question.
Well, let's see if I can find her.
Great to see you, Kara.
Hopefully she's able to do it. Hold on, I'm looking, hold on.
Oh, do you have to physically unmute her?
I think so,
Oh,
yeah.
okay. Well,
I-
Kara's saying dead brood produces different signals, and so dead brood produces different signals than the diseased brood. And so, in the case of UBO, it's a synthetic pheromone that mimics diseased brood, and so it's thought to be more reliable of a way of finding bees that confer disease resistance than to test bees' ability to remove and to detect and remove dead brood.
Her mic is on now in case she wanted to pop on live. If not, I think that's a good answer.
Go ahead, Kara.
Hear me?
Yeah.
There you are.
Great. Yeah, so there's some work from McAfee. I've not tested the signals from dead brood, but they do produce different compounds, oleic acid, beta-osamine. There's some work from McAfee on dead brood signaling, but it is different from the signals from unhealthy brood. That was the question, right? Did I
Yes.
understand the question? Okay.
Yep.
Yeah. Thanks,
Thank you,
Kara.
Yeah. Sure. And so we're doing a little bit more work to figure out kind of the other side of that, the detection of those odors in terms of odorant binding proteins on the antenna. But I think we'll have some more results on that in the next, hopefully a couple of months or so. But it looks like UBO selected bees have more odorant binding proteins that detect unhealthy brood signals, whereas freeze kill brood selected bees have more odorant binding proteins that detect those dead brood signals, which makes it.
Thank you, Kara. Appreciate you.
Sure.
Dr. Alger, so a lot of the individuals that are here today are curious in the overlap and contrast and comparisons with the HARBO assay. And with the group that you're working with in Vermont, are any of those beekeepers, you said some are using freeze kill, but are any of those beekeepers within the cohort or that you guys have interacted with throughout the course of the program using HARBO assays, sort of a contrast with the UBeeO assay?
The beekeepers that I'm working with are not using the HARBO assay. But I don't want to put Kara on the spot. But if she wants to chime in with any of the experience that all the beekeepers that she's working with or her collaborators, she's welcome to comment on that.
We're gonna get her and give her.
Oh, okay, great.
Yeah, we'll
All
get
right.
that could be a whole other talk, I think.
Okay, great.
There's definitely some
if
data
there's
there.
anything,
Yeah.
we haven't done it. But I welcome if don't feel bad about speaking up, Kara, if you want to chime in with what you know, but that's fine.
On your UBeeO
They're correlated, but they're not the same. I'll just say that. Keep it brief.
Thanks.
She said it. So are you seeing a high correlation of overwintering success with high UBeeO scores?
Yes, we're seeing more higher UBeeO scores are more likely to overwinter. Their Varroa loads are lower. Their virus loads are lower. Yes. In the beekeepers that we've worked with in Vermont. Yeah.
Let's see. Does the priming for UBeeO include pollen, or was it just sugar water?
The priming. Oh, okay, yeah, because I was saying pathogen priming, which I have to. To try to improve the reliability of the UBeeO assay during a nectar dearth, the recommendation is the sugar water up to a week before the test.
Were your high UBeeO colonies treated? Were you using treatments on the high UBeeO colonies?
No, they weren't treated unless their mite loads exceeded the threshold, and then we had to treat. And then they were removed from the program for that year.
What was your threshold?
2 mites per, well, It was 3 mites per bee, and then we in the first year, and then we reduced it to 2 mites per bee. Or, sorry, 2%.
2%.
Mhm.
All right, let's see. I think we got some other much longer questions. But
Okay,
yeah, we're gonna have to transition to our next speaker. If you wanted
sure.
to answer those in the chat, you have access to that. We'd be very grateful. Thanks again for coming. I'm glad we were able to finally have you on. It's been a few months, almost a year in the making. So
Yeah, thank you for
yeah.
thanks for your patience and having me on.
Oh, 100%. It was well worth it. Thank you again.
All right.